This is an introduction to NMR. NMR, or nuclear magnetic resonance, identifies hydrogens and carbons present in the molecule. It's a very powerful tool for elucidating structures of compounds in organic chemistry. Proton NMR determines the number and type of protons in a molecule, while carbon-13 NMR determines the number and types of carbons. The underlying principle of NMR spectroscopy is nuclear spin, and this is what makes atoms visible by NMR. In order to be visible by NMR, an atomic nucleus should have an odd mass number, or an odd atomic number, or both odd numbers. When we say an atomic nuclei has spin, we need to remember that the spinning nucleus causes a magnetic field of its own. While we focus on proton and carbon NMR in organic chemistry, we can also do NMR with other spin-active nuclei, for example, phosphorus-31 or nitrogen-14. We talked about the basis of NMR spectroscopy, and we said that it depends on nuclear spin, and spinning nuclei create their own magnetic field. In the absence of any external field, all these nuclei are randomly oriented. Now, if we apply an external magnetic field, and we assign that as B0, at that stage, the nuclei have the choice of aligning with the field, and that would be a low energy state, or aligning against the field, and that would be a high energy state. The difference between the low energy state when the nucleus is aligned with the field and the high energy state when the nucleus is aligned against the field is denoted as delta E. In an NMR instrument, we apply an external field, B0, and then we apply an external energy to match delta E. This gives the nucleus enough energy to flip from the lower energy state to the higher energy state, and we say that the nucleus is in resonance. The nucleus then flips back to align with the magnetic field, and in doing so releases the same energy. And this is what gives the signal that is measured by the instrument. Now, if every proton had the same delta E, we would receive only one signal in the NMR spectrum. We're lucky because every proton is on a molecule that also has electrons. Moving electrons create a magnetic field opposite to the externally applied field, and that shields the nucleus from the full force of the externally applied field. So, the B local, that is, the local magnetic field felt by every proton, is going to depend on its electronic environment. Spectrometers will keep B0 constant, and the local field will be B0 minus any field that's set up by the electrons. This gives every proton a unique magnetic field, and that results in a different delta E for each proton. If we have a different delta E for each proton, they will release signals at different positions in the spectrum. These signals are represented by the chemical shift, or delta, and the unit for that is parts per million. Two terms that we commonly use to describe protons are shielded and deshielded. A shielded proton has increased electron density around it, and so it feels a decreased local field. And this in turn is expressed as a decreased chemical shift in the NMR spectrum. A deshielded proton has decreased electron density around it, and therefore it feels a stronger magnetic field. This is expressed as an increased chemical shift. The result is that each proton will resonate at a different frequency due to its local environment, and this is what makes NMR so useful because we can distinguish proton signals in an NMR spectrum. This is an example proton spectrum, and you can see that the chemical shift ranges from 0 all the way up to about 12. The scale is measured in ppm, and you can see that shielded protons will appear at a lower ppm, while deshielded protons will appear at a higher ppm. In terms of the spectrum, we call it upfield, where the protons are more shielded, and downfield, where the protons are more deshielded. Each of these peaks corresponds to a set of equivalent protons, and each signal also has a different pattern. For instance, this peak around 9.6 ppm is a singlet, whereas these two peaks are divided into two peaks each and are called doublets. So a proton NMR provides far more information than just chemical shift. The chemical shift provides information about the local environment of a proton, while each of these signals also provides information on its neighbors as well as how many equivalent protons there are.